Now, student will apply the Biot-Savart law to find magnetic induction at different situations. We'll take a first example. We'll take a circular coil, and that coil carries a current I. The I current is flowing through the coil. And what is the magnetic induction at the center of the circular coil? That is what is our discussion today. Now, so this is the thing, and we have to find the expression for this. So let us consider a circular loop with this at the center, and I is the current that is flowing through this. Now, what is the magnetic induction at this center? That is what is our concern. Now, we'll use Biot-Savart law that we can apply by introducing the law, that is from Biot-Savart law. We'll write that dV I'm writing this in scalar form because I know the direction of magnetic field. If I know the direction of the magnetic induction, so I just can find the magnitude. For a straight conductor, we hold like this. For the circular coil also, we hold like that. For a circular coil, to find the direction of magnetic field that comes out of the coil, the coil is like this in this plane, current is flowing like this. Here, our curved fingers of right hand must be in the direction of the current in the coil. The current is anti-clockwise. I will curl my fingers in anti-clockwise sense. The thumb must be in the direction of the magnetic field. So the direction of the magnetic field will be like this. So the direction of magnetic field will be like this. So from a circular coil, the magnetic field will be pointing out like this. And we know that magnetic field is a complete loop. Magnetic field exists in complete loop. So it goes like that, and again it comes back like this and enters here. So it's a complete loop. What we are studying is only this part, that it comes out like this. It comes out like this and enters from below like this. It's a complete loop. It's a complete loop. That also you can imagine by, so it is like this, something like this. I'll just show you here. The current is like this. It will be like this, and it will go like this and complete like this. It's a complete loop. So only we are concentrating our focus, in our attention to this part only. Okay, it behaves like a bar magnet, as if a bar magnet of North Pole and South Pole is kept here. We know that from North Pole the lines of forces come out and then enters through the South Pole. Similarly, this side it is like this. So the magnetic field lines are exactly similar as in the case of bar magnet or in the case of coil carrying current. If I revert the direction, then this will the arrow will change. That means the field which is like this will become like this. So it will enter from, now it is entering from below and exiting from, coming out from the above, but then it will be reversed if I change the direction of the current. Thus similarly, the change the pole, that will change. You can also say that if I take a loop, I take a small part of the loop. This is a coil. I take a small part, which make this loop. That small part is a conductor, straight conductor, just like this. Okay, conductor. So small conductors. These small conductors then complete the coil. If I concentrate on the small element of the conductor in the straight line, then if current is like that, then I will hold the conductor, and this is the direction of the magnetic field. Hold it like this. This is the direction of the magnetic field. So from inside the coil, the lines of force will come out, whether the element I choose is here or here. If I choose here, then also it will come out. Hold it like this, come out. So from this part, the magnetic field will come out, just like this. So from this here, it's only coming up, and all will get added up. Why they will get added up? Because all the directions are vector and directions are same. So we will not draw all the arrows coming out of because of the contribution of individual elements. We will just say that because of the coil, so whatever the resultant, that we will consider to be in this direction. We will consider only one. So if so here also the magnetic field will be like this. This is the direction of magnetic field, and our aim is to find this induction, to find the magnetic induction at the center of coil. This is the direction. Now I am interested in the magnitude part. What its value that comes out to be? Coil which carries the current I, whose radius is suppose R. This radius is suppose R. Then I. This is written for the small element of length dl. This length is dl. The current flowing is I. So this ideal is a vector, and this is also a vector. It's a point where I have to find the magnetic field. This ideal is like this. This is tangent to the shape of the conductor at any instant. So the shape is like this. This section, this will be the tangent. This section, this will be the tangent. This section, this will be the tangent. So you have to draw a tangent for a circle. For a circle, at this point, this is the tangent. This is the tangent. This is the tangent. This is the tangent. So for a circle, the radius and the tangent drawn always make an angle of 90 degree. For any circle, this radius and the tangent drawn make an angle always of 90 degree. So the angle between these two vectors, that vector R and the vector ideal, the angle is 90 degree. That means theta is 90 degree. So this theta, which stands for the angle between the two vectors, it is 90 degree. If that is 90 degree, then we will proceed for the, this will become 1. So mu 0 upon 4 pi ideal upon r square. So dV becomes mu 0 upon 4 pi ideal upon r square. But that is the magnetic induction due to the element that we have chosen. That is because of the contribution by only dl element. But I want the magnetic induction due to the whole of the vector, whole coil. Then I have to consider each such elements and then add up, because the direction is same, just scalar addition. So that means we use integration. If I take integration of this on both sides, that will give me B. This is the magnetic induction at the center of the coil. That comes out to B. Integration of this, but this R, as you change element, I is not changing. For each element you choose, here or here or anywhere, the same current I will flow. So I is constant, taken out. Mu 0 upon 4 pi are their constants. I is now taken out. As you change the element, R is also not going to change. You can see here, R, the magnitude part of R is not going to change. R as a vector will change, but the magnitude of R will not change because we are writing the magnitude form. R magnitude will change, not change, but this direction will change, and we are concerned only with the magnitude part. So the R will remain same, that also is taken out of the integration. Only we are left with DL integration. But this DL will move from any point you start from here to go all the way along the circumference and comes back to the same point. Then only your coil will be complete. So therefore, you have to integrate this from this point, suppose 0, I'll move around and come back to the same point. So I have to cover a distance of 2 pi r. The elements are, the length of these elements are distributed from 0 to 2 pi r. Why 0 to 2 pi r? If you take a coil and cut it and make it straight, then this length will be 2 pi r. This point is suppose 0, then it spreads up to 2 pi r. So I have to consider element along the length of this. So therefore, my integration will be from 0 to 2 pi r, because within this only I will have my elements. So therefore, 0 to 2 pi r is the integration. Now, mu 0 I upon 4 pi r square, dl integration is L. Okay, now you know how to find the definite integration. This is upper limit, this is lower limit. Put this limit first, then put limit is second and subtract it. So 2 pi r minus 0, 2 pi r. So this is so 4 pi, 2 pi, 1 r will cancel, 2 pi is here, I divided by r. 1 r will cancel, 1 r is left, there is no r over here, 2 pi I is over there. So this is the magnetic field at the center of the circular coil. So this is the formula. This formula to remember, mu 0 upon 4 pi, 2 pi I upon r. Now, if the question is of any section of the coil, semicircular coil, if I have a coil like this, so the semicircular, so this is the center, suppose this radius is r, but now it is a half circle, not a full circle. Then if I ask you to find the magnetic field here, B, due to half circle, then how much is this? Full circle is this, half circle will be half of that, because we are adding finally. So it should be, by logic it should be mu 0 upon 4 pi, 2 pi I by r, it is because of the full coil, half coil means divided by half. So this comes out to be mu 0 upon 4 pi I by r. This is for a semicircle. This is correct. If it is 1/4 of the coil, this is case 1. Let us take one more case. It is like that. 1/4 of this is r. 1/4. Then you will write 1/4 of the full circle. That means B 1/4 part of the coil. This will be the case. The full coil you take and divide by 4. That is correct. The answer comes out to be this will be the answer. If I say it is 60 degree, then what? If it is 60 degree, then what? So you can equally divide. So we have to derive a logic. See the logic. then we'll use that formula for any section, any fraction of the full coil, whether it is half, 1/4 or any part of the coil. The formula for full circle is, this was the formula that I will show you here, 0.4 pi 2 pi I by r, right? You can see one thing when you cut this value. So for the full coil, the total angle is 360 degree or 2 pi radian, therefore it is 2 pi. When I take half circle, it is pi, so it should be, in place of 2 pi, it should be pi. So that is what is the answer. You can see here, this is pi. When it is 1/4, this angle is pi by 2, so this is pi by 2 I by r. I by r is always there. That means what? That means I write the general expression if I want. For any angle theta, the theta comes here. If full circle is 2 pi, if it is theta, theta will come here. The general expression, so general expression for any theta is mu 0 upon 4 pi this is the general expression. This theta, here it is 60, so for this, the answer should be for 60 degrees how much radian? Pi by 3, okay, pi by 3. So the answer will be I by r. Theta you substitute pi by 3. Here theta is pi by 3. So this values here, you will get the answer. We have already known that mu 0.4 pi always in the numerical comes out to be 10 raised to minus 7. And the unit I have already told you that this is Tesla, magnetic field, Tesla, and this is meter per ampere. So this is what is the value. If I have more number of coils in place of one coil, if I have two coils, then what? Case number 3 here. This is general expression. Now case 4. I have a coil like this, and I take one more coil of same radius over it. But if I draw it over it, you cannot see. So I will just distinguish for the sake of distinction. I will draw another coil in its vicinity just to distinguish. If I is the current in the first coil and I is the current in the same coil, second coil also, and the same current is flowing through both the coils. How is it possible that you have to have the current like this? Yes, it's possible. You can have a coil like this, again one more round like that. So just in case of a solenoid having more number of turns. So it is a matter of spring-like structure. One coil goes like that, another coil. So the number of turns that you can increase, you must not keep in mind that this one coil is lying over the coil and they are not insulated. They are insulated. If they are not insulated, they will give like a single coil. Okay. So one coil, another coil, they have to be insulated, or there should be separation, just like a spring. Then it will be number of coils. If there are two coils, then we have This is what is the magnetic field due to one coil. So I have to add plus this again, and means it's 2 times, because contribution from one coil is this and contribution from another coil is exactly the same. So you have to add the 2 numbers 2 times. You have to add the 2 numbers, so it is twice of this value. If I increase the coil to number 3, then 3 times this. So in general, if it consists of n number of coils, so if n is the total number of turns, then B equals to magnetic field due to n turns of the coil is n times the value. That means this is the coil. Okay, and if there is a coil of radius say A, I'll take another coil of radius B. This carries a current I1, this carries a current I2, but the direction of current are not same. One is anti-clockwise, the other one is clockwise. Then if I ask you what is the magnetic induction at the center of this coil, obviously the contribution is very much individual. Each contribution due to the first coil at the center and the contribution to the second coil at the center, you have to add them, but this addition should be vector addition, because TB is vector, so you have to have vector addition. So in that case, you have write the contribution by this and then by this. You can take any sense as positive and any other sense as negative. I'll consider this clockwise as positive and this anti-clockwise is negative. So this minus this. Okay. So contribution from this coil is say B2. Contribution by this coil at the center is say B1. At the center, due to this coil, the magnetic field will be upward. Due to this coil, it will be downward. So due to B, it is downward. Due to A, it is upward. I have taken this cross as positive and the dot as negative. So this sign will automatically get attached to this B1 and B2. So my total induction at the center will be B1, B2 minus B1. This B2 is I2 upon B minus should solve this, you'll get what is common? 2 pi common, so I2 by B minus I1 by A. If current is same, that also will come out 1 by B minus 1 by A. So this is the answer to this question. So it is not that you add only. These two coils are added because they are in the same directions. This plus this. Here you have to take subtraction because they are in opposite sense. One magnetic field is going up, another magnetic field is going down. So the two vectors, one pointing up, pointing down, you take a subtraction. When both the coils are producing magnetic field in the same sense, you add them. Okay, thank you.